we have a presentation from our very own organizer, Andy, about temporal graph analysis with TGX. Andy, Shenyang Huang, is at McGill University and at MIDA. He's a PhD student, and he focuses on temporal graph learning. He's supervised by Professor Raihani Rabbani and Professor Guillaume Rabousseau. He is interested in representation learning on temporal graphs, anomaly detection, and graph representation learning. And he was the organization chair for the temporal graph learning workshops at NeurIPS in 2022 and 2023. Previously, his research included change point detection on temporal graphs, COVID disease modeling with temporal contact graphs, and link prediction on temporal graphs. He also enjoys writing Medium blog posts and temporal graph learning. And yeah, we're looking forward to your presentation.
Great. Thanks for the introduction, Julia. So let me share the slides. So if you want to follow, and also all the links is in the slides. So if you want to follow the presentation, you can see here. Let me find the chat tab. And I will be sharing my screen. Okay. Can you all see my screen?
Yes.
And I think I will make you co-host, Julia, so you can add people when they join, because I'll be presenting to them. I just need to find you. 1 second. How do I will make you host. Yeah. Okay. So I will minimize this window here. Yeah, so thanks for coming to the presentation today, everyone. So I'll be presenting our recent work called Temporal Graph Analysis with TGX, which will be to appear in the Wisdom 2024 demo track. And this is a joint work by Razieh, me, Elahe, Rehane, and Pharma. And you can find the link to the paper and the link to the GitHub here. And we also have a pip install of the package. Yeah, so here's the outline of the talk. So I will start with some introduction on the motivation for the package. And then I will go over the high-level pipeline of the package. Then I will show some data sets and how to load the data sets in the package and how to generate the network statistic and visualization. And lastly, this is planned to be a community-driven project. So we can look at like different future directions together and then try to build a more feature-rich package together. So as a mandatory introduction slide, temporal networks are ubiquitous. So we have different types of network in the real world, including the Amazon Review Network, the Wikipedia co-edit network, the cryptocurrency transaction network, human contact network, and LinkedIn social network, for example. And on the right is one example of a social message network. And as a background for this talk, I want to first talk about how do we represent temporal graphs. And some of you might be familiar with this, but I will go over the details because it's important for the code part as well. So we have two different categories of temporal graph representations. One, which is the earlier category, is called discrete time dynamic graph. So here you have basically you treat temporal graph as a sequence of graph snapshots. And you assume that these graph snapshots, the graph structure itself, is sampled at regular time intervals in time. So that means that you will get one graph snapshot today, tomorrow, and the day after tomorrow, for example. And the time granularity of the discrete time dynamic graphs can be hourly, daily, weekly, monthly, and so on. And the other category of temporal graph, which gains more traction recently, is called continuous time dynamic graph. So this is supposed to be a more general representation of temporal graph where the distribution of the edges might not be as regular, and the graph is modeled as a stream of edges that can arrive at different time in the future and at irregularly sampled time timestamps. So so for these data sets, they are usually represented with the Unix timestamp. And one thing that we want to do in this package is to allow the data loading of continuous time dynamic graph data sets, and then you can then discretize them into discrete time dynamic graphs by remapping the timestamps. And then once you have the snapshots, then you can look at some graph statistic as different snapshots over time. And here are some challenges with trying to analyze temporal graphs. And for some of you that have tried this in the past as well, this is a very challenging process. So for example, most existing packages that are well developed, such as Network X, is designed for static graphs. And how to visualize temporal dependency between entities in an open problem. So, so usually try to visualize graph is already difficult. And now you also want to like visualize the temporal dependency or the temporal like neighborhood between nodes. That's even more difficult. And we also want to understand the statistical properties of temporal graph. This is important because many of the temporal graph methods would actually behave differently based on different statistics of temporal graph. So for example, in the TGB work, we show that the ratio of test edges that you don't observe in the training set would actually have a significant impact on the performance of the models. And different type of models would perform differently depending on how the edges arriving in the data set, and also how novel is these edges, and so on and so forth. And you also like often require the customized code and redundant code also on trying to load new networks and try to visualize them. And one last point, which is one of the key features of this package, is that it allows you to discretize the data into snapshots such that you can visualize the trends over time. So the bottom is one example plot where we visualize the number of nodes and edges from a data set. And there's a question in the chat.
Yes, the question is, how is the discrete time graph represented? As in, what is the data representation of dt/dg?
So the data representation of dt/dg and for continuous time is the same in the library, where we basically represent the data structure, the core data structure, as a dictionary of snapshots. So basically, you have the time as the key to the Python dictionary, and then you have the edge list, which is like all the edges, also stored in a different like dictionary. So you basically have time as the key, and then the edges as the items, like all the values like of the dictionary, and you basically have these like as snapshots. Yeah. So so this allows you to like very quickly query different timestamps and retrieve them. Okay, thanks for the questions, and feel free to send questions in the like in the chat, or like interpret me if needed. Okay, so here I will provide an overview of the TGX package. Oh, we have more questions. Okay, I will quickly go over the package. So one question is there visualization of the evolving process of dynamic graph? So here for now, we are mostly looking at the graph level like statistic. So so you can look at how the number of edges changes over time, or then the node degree change over time, and we also provide the edge traffic plots from our previous work in 2022, where we look at how does the recurrence of edges look like in the network. And these are shown in the T and TED plot. And in the future work, we can like very easily add more visualizations to support more nuanced like visualization of the evolving process of these network. And another question is, do the relations also change in nature or is the relationship between the nodes the same always? So so here, like as a first step, we would model the homogeneous temporal graph. That means that the relation type between nodes like will be the same. So for example, between all the nodes, they will be sending messages to like to each other. However, like real world data can also be heterogeneous, where you can have different types of interactions between nodes. So that will be like a different data type called temporal heterogeneous graph, and that would be that can be added like as support in the future. But the like just on the edges themselves, the relationship between nodes can also change over time. So like for example, like you think about a citation network, the way that you publish in the first few years of PhD, like versus your later years in PhD, like will be quite different. So you might have more collaboration patterns later on. Like well, in the early stages, you are mostly just focused on the core like thesis projects, for example. Okay. So I'll go back to the talk. So here's the pipeline for the TGX package. So basically, you start with the data loader, and the data loader is basically have three different data sources. So we have the built-in data set from our previous DGB work, which supports around 13 networks or 12 networks. Then we have the TGB datasets, which can also be directly loaded into data loader. So that supports all the datasets from TGB. And you can also load from the custom data, which if you specify your edge list, your temporal edge list in a CSV file, then you can then you just need to specify like which column is the timestamp and which column is the source and destination and so on. And then once you load the data set, then you would put it into a TGX graph object. And in this graph object, you can perform time discretization, as I mentioned. So you can you can chop up your temporal graph into discrete snapshots based on how you want to analyze it. You can also do subsampling of the nodes. So you can like specify like which subset of nodes that you want to sample, or you can randomly sample the nodes if your data set is large. Then you can compute the visualizations. So we support the different edge traffic plot, as I mentioned, as well as the graph level statistic, like the average node degree, the number of nodes and edges, and so on. And these statistics help you understand how does the network statistic evolve over time. And then you also have some other statistic that we have used in the previous work as well. So these are more looking at basically the recurrence or the surprise. So these are the like the edge like level statistic, and I'll get into that like later on in the talk. And you find and you can find a link to the paper and GitHub and the documentation website here. Okay, so so I briefly talk about the features in TGX. So we basically provide a standardized data loading and processing for both continuous and discrete data set. And now basically like you can go from a continuous data set to a discrete data set. Note that in terms of the representation, the key difference here is that for continuous data set, the timestamp like will be stored as a Unix timestamp, and then for the discrete data set, you will then remap your time intervals into like integers. So starting from 0, 1, 2, 3, 4, and so on. And in the function, we also allows you to store the remapped like Unix timestamp if you need it. And we support like around 20 temporal networks out of the box from both TGB and DGB. And you can also load your custom datasets. And we provide the discretization functions to go from the two different representation. And then we provide the statistic and the visualizations. So there's a question in the chat. do you provide time encoding functions? No, we don't currently provide the time encoding functions, but that's definitely something that can be very easily like added in the future, and you can add it as part of the data loading, for example. And here as here's an overview of the datasets supported in TGX. So we have 6 different distinct domains, and we have the built-in datasets. So these are different datasets. Some have like the continuous timestamp. Some is on the different granularity, such as like yearly or monthly and so on. And these are like smaller scale datasets that are faster to get started with. And we report these statistics in the paper as well. Here you can very easily compute the surprise index or the recurrence index and so on and so forth. And for the TGP datasets, we support all the TGP datasets, like including the newest dataset from the no property prediction that we added in the late last year. So you can like look at the discretized version of these datasets and use them to analyze how does the network change over time. And in terms of the data loading, so basically there's three simple steps, or 2 simple steps. 1 step is optional. So you would first load your dataset. As for the TGP datasets, it's very simple. Like you will just do tgx.data.tgb, and then for the built-in dataset, you will do tgx.builtin.the dataset name, and then you can also like use the read CSV function to load a custom dataset that you have locally. And for the graph objects, which is the core object of the library. So here you would feed your dataset that you have loaded, which is the the edge list format or the data name, and you would feed it to the graph object, and this will then convert it to the continuous time dynamic graph, which then which then you can discretize to the discrete time dynamic graph for the visualization. And optionally, you can also subsample the graph by random selection for now, for example. And you can find this in the tutorial on the GitHub. So just to talk a little bit more on the high-level idea about the object in the package, and then I will go into the live coding part later on. So the TGX.graph is really the core graph object. So as I mentioned before, some of the key component of this object is the data object, which basically stores the edge list information in a dictionary format. And if you want to export it for downstream machine learning task, you can just do graph.export full data, which will then basically give you the temporal data object in PyG, like in the NumPy format. Then you can convert it to the PyG format if you want to. So this will give you a dictionary with the keys being the source, destination, and timestamps, and each one will store the NumPy array version as the corresponding value. And lastly, you can do the discretize function where it's very straightforward. You will just need to specify the time scale. So what time granularity do you want to? And if you want to store the remap Unix timestamps. So here you will get a new graph object that is separated from your original graph object as the discretized version, as well as the timestamp list if you want that. So Yeah. So then with that new graph, then you can do more visualization on the discrete data set. So there are two resources that we already provide as a tutorial. So you have the data loader, which we just saw. That will teaches you how to load the built-in data sets as well as the custom data set. And then we have a separate tutorial for the network visualization and statistic. So here are all the visualizations that are currently supported in the library, and we plan to expand this in the future. So you have the degree over time, the node and edges over time, as well as the number of connected components per timestamp, and the degree density, and the T and TED plot. So here are some example visualization. So here we're plotting the number of nodes and number of edges in the same plot, and you can see how their trend will be overlapping with each other. And here you have the daily node degree, where you are plotting the like the average node degree over time. And here you have a t-plot from the wiki dataset when you discretize it into daily. So these are just a few of the functions. Then we'll look at the statistic. So we support these current statistic for now. So we have the recurrence, the surprise index, and the novelty index. So these are important to understand the edge level statistic. Then we also have the average node activity, the size of the connected components, as well as node engagement. So here are the definitions for the novelty and recurrence and surprise. And you can find this in our previous paper as well. And these are documented in the tutorial here. So I will go to a live collab. Is there any question for now? Okay. So can you see my screen?
Yes.
Okay. So basically, like you would start by installing the package. So you would just do pip install, and then once you have installed the package, then you would import TGX. And if you want to use the TGB datasets, you would also need to install TGB as well. And then you can select which dataset that you want to visualize. So for the TGB datasets, you can specify the dataset name, and for the built-in datasets, they are encoded into the function name. And these functions will automatically download the datasets if you don't have them. So you can just run these to retrieve the datasets as well. And then the first step is you would put your datasets into a graph object. So you will construct it as a continuous time dynamic graph. So for the experiment here, so let's just run it on the wiki dataset, for example. So I will click this. And because I've already downloaded this, so we'll just load it. And then here you would first load it to the graph object. Then you would specify if you want it to be daily and weekly and so on. Then you will get a new graph that is the discrete version, which we'll call the DTDG for this tutorial. So now you can visualize the features on the discrete graph. So here, the first plot that we're looking at, let me maybe zoom out a little bit. The first plot that we're looking at is the average node degree over time. So we can generate a plot on the fly here. So here you can see like the axis being the average degree, being normalized, and then the timestamp in the x-axis. And then you can also plot, and the red line, I believe, is the average. Is the average across the entire time span. And you can also plot how the number of nodes change over time. Yeah, so this is a different plot because like we're using the wiki data set. So this actually looks very similar to the one that we have above, though with like with some small differences. So here we're tracking the active number of nodes. So the nodes that actually do have edges. And we can plot how the edges look like. Again, very similar to the node, but this might not be the case for like for each data set. And we can put them both in the same plot, and you can compare the trend. So so indeed, they look very similar in terms of how they are correlated with each other. And then you can also compute the number of connected components. And here, like we see that like the graph is actually getting more disconnected over time as new nodes are added as well. And this is the density plot, a heat map of the node degrees per each of the snapshot. And we can also generate the edge traffic plots. So here for the T plot, we are showing for each of the snapshots how much of the edges are the repeated edges that we have observed in the past, and how much edges are the new edges that we that have just arrived in this snapshot. So here we can see that for each of the snapshots, there's actually a quite consistent portion of edges that are brand new, and roughly more than half of it is repeated. And for the edge traffic plot, this will take a little bit to generate. So we'll come back to this one, but basically this plot visualizes how does the edges like reoccur. And you can also look at it based on the train test split. So here we are defining it like as 15% for the train and test split, the test being the 15%. And you can also very easily compute some statistic. So so you can look at the different index that we talked about before, like the reoccurrence and surprise and novelty. You can compute them here once this one is finished. And you can also look at the size of the connected components, how that changes over time, for example, or the different node engagement, and so on and so forth. Yeah, so while we are waiting, is there any question?
There is one in the chat which says, so the temporal graphs are like 3D networks having both spatial and temporal dimensions.
Yes, you can think about it that way, but like I like to think about it as your timestamps or snapshots are the temporal dimension, and the temporal dimension can be smooth or very like or very irregular, such as in the like in the continuous time, and your spatial time like your spatial dimension is basically your graph structure, like represented as a like as the adjacency matrix. However, these are like relational, so there's no inherent notion of what is more adjacent to another, like beyond the edges that they have. Yeah. And the plot is done. So here, this is the TED plot. So basically, for each of the edges that do show up, the little dotted lines that are going up is basically showing how these edges like reoccur over time. And you can see that some of the edges do reoccur much more frequently than the others, while some of them is completely empty. That means they only show up once. And the edges are sorted by the order of which they appear in the network. Okay, so we also got the plot from the statistic. So here for some statistic that you need to specify the test ratio, you can just input it to the function, and you can very easily compute it. And here is the size of the kinetic components. So this is a different statistic than a number of components. This shows the largest size, which we can see is quite consistent over time as well. And you have some other statistics such as the node engagement as well. So this notebook basically shows the currently supported features in the library, so you're welcome to use library for the preliminary analysis of new temporal graph datasets, or just play around with the supported datasets that we have in the paper. Okay, so I will talk a little bit about the future directions that we can take. So if you're working on different temporal graph statistic, or you have ideas on how to incorporate more insight into the package, so we're hoping this to be a community-driven project, so we can work together to add more features to the package and make it easier to use and for more diverse use cases. So some of the future direction is for example, adding support for temporal graph motifs, or try to add some statistic based on the random walks on temporal graph. And another very useful functionality is to add some community detection algorithms on temporal graphs, and as well as some of the evolution of the spectral properties. Another point is to add some visualization of the graph itself. Though this is more challenging because you have the temporal dependencies, but if you can visualize the nodes and edges similar to the network X and the Jiffy, that would be great as well. And lastly, we can add support for the edge features and node features, as well as more data set built into the library. So if you're interested in contribution and collaboration, please reach out to us, and you can find our email and website here. Okay, so that's a very quick overview of the package, and for the paper. So feel free to ask any question as well. Okay.
Hello, thanks. I have a question.
Yes. You can go first, and then we'll go for the ones in the chat. Yeah.
Oh, sorry. Okay, thanks very much for your excellent presentation and also this excellent communication-driven project. Currently, I'm working on link prediction on static text attribute graph, and most of the state-of-art technologies is varies from the benchmark and data set. Some of them are embedding method, or some of them is heuristic based. And most of the famous works they actually based on the structure optimized graph neural network. So, which leads to my question: is there any capacity that we can adapt the current state-of-the-art technology in this via benchmark data set in this library?
Sorry, can you repeat the question?
My question is, is that in your future plan to adapt the current state-of-the-art technology on static graph into this library?
So for the moment, this library is built to be a statistic and visualization library. So it kind of serves as more of the data analysis and data loading part of the machine learning pipeline. But like in the future, that's possible to have a library that's more focusing on the methods, and can use the TGX as a data loader, for example.
So thank you very much.
Yeah, thanks. So also the question in the chat. So does this package support larger than memory graph, like 1 billion plus nodes? Is there a batching or lazy evaluation? So at the moment we haven't tested for the larger than memory graphs, but I think it is possible to be implemented in the future. So I think increasing the efficiency of the library on the backend data structure can be a very important direction. Do you guys also need further node embeddings with time information? I'm not sure I exactly get that question. The node embeddings will be computed for temporal GNNs. The node embeddings are computed based on the timestamp that you kind of retrieve it. So the node embeddings are changing over time, if that's your question. And yeah, so thanks for coming to the presentation. Have you linked any temporal GNN model with library? So currently for my own research, I've been just using the TGX package as a backend for data loading, and it works quite well. So for example, you can get all the temporal edges in the get full data function here, and that helps you to then reshape it for the downstream machine learning models. But no, the current package is not focused on the machine learning part. Though we do provide a lot of the baselines and examples in the TGB library, where we show how to run the state-of-the-art temporal graph models. So so if you're interested, you can find it in our previous work here. I'll just share this link in case it's useful. Yeah, so you can find how to run there. Oh, let me share to the group. Thanks. Do you allow multiple overlapping networks to be analyzed? So currently we don't analyze multiple network at once. I think it's a very interesting direction. But so you can look at the the plots jointly. But I think in the future it's possible to have some plotting functions that can overlap the networks on top of each other. But that would be a new functionality to add to the library. So I think there's a lot of potential in improving the library and to make it more usable for different use cases. So thanks for all the questions, and then let's build a library together. Yeah. So if you're interested to help add different functionality to the library, just email me and we can discuss how to work on the code together. No, there's no current scene temporal graph and video-based temporal graph data sets, but I do think that it's a very interesting data set category. So we have so if you would like to contribute these data sets, so we're happy to include them in the package as well. So feel free to reach out about that. So for now, the network domains is mostly it's mostly on the on the interaction networks, and the social networks and the politics network and transportation network, for example. Yeah. Okay. Yeah. So thanks for coming to the presentation, everyone, and thanks for the many questions and so on. And if you run into any like issues while like using the package, feel free to raise an GitHub issue, and we'll look at it. Yeah, so let's build this library together. Thank you. Thanks, everyone.
Thank you.